Dear students, before considering the condition for stability and stationarity of VAR, to refresh your memory, let me first refresh the condition for stability and stationarity in a univariate context. This is what we have already discussed. So it is only a repetition of what we have considered earlier. Now consider an AR2 yt is equal to phi1 yt minus 1 plus phi2 yt minus 2 plus epsilon t. And using the log operator, we write it as yt is equal to epsilon t. The constant is not considered here, not a problem. Now this can be written as phi L yt is equal to epsilon t. Now, the stationarity or the stability of this AR2 process depends on the roots of the polynomial 1 minus phi 1L minus phi 2L square. That is the value of L which satisfies the condition that is equal to 0. As it is a second degree polynomial in L, you will get two roots, L star 1 and L star 2. Now the stability, the stationarity depends on value of these roots. As we have discussed earlier, the stationarity of an AR2 process depends on whether the roots have modulus, absolute value greater than 1. Now, let us consider a case in which phi 1 is equal to 0.75 and phi 2 is equal to 0.25. So that substituting the values, you will get 1 minus 0.75 L minus 0.25 L square equated to 0. This can be factored as 1 minus L into 1 plus 0.25 L equal to 0. The solution will give L star 1 as equal to 1, L star 2 as equal to minus 4. So the process has two roots and one root is 1. The other one has a modulus greater than 1. So if you extract this one unit root, you can model this as a stable process. And this is achieved by first difference. So for example, we can write it as this as 1 plus 0.25 L into 1 minus L yt as equal to epsilon t, or 1 minus L yt is delta yt is equal to minus 0.25 L yt, that is minus 1.25 delta yt minus t, delta yt into L plus epsilon t. Now as you can see, the model in first differences is stable, stationary, because the value of phi 1 is minus 0.25. The condition for stationarity is satisfied. So the model in first difference is stationary. Now consider another case. Consider another case. Now suppose that 1 plus 3l minus 4el square yt is equal to epsilon t. That is phi 1 is minus 3, phi 2 is 4. Then this will be factored into 1 plus 4l into 1 minus l yt is equal to epsilon t, which gives the roots l star 1 as equal to 1, l star 2 as equal to minus 1 by 4. Now the process has two roots. The process has two roots and this is delta yt. So delta yt is equal to minus 4 delta yt is equal to 4l delta yt. So minus 4 delta yt minus 1 plus epsilon t. So the process has two unit roots. Both have modulus less than 1 minus 1 by 4. So the first difference is again non-stationary. That means you have to difference the series 2 times to make it stationary. First difference is not stationary. You have to make it stationary by differentiating 2 times. This we have discussed earlier. So whether an ARP process is stable or not depends on the roots of the characteristics polynomial. If all the roots have modulus greater than 1, the process is stationary. If one root is equal to 1 or less than 1 in absolute value, then if you extract this root, you can model the series in stationary as a stationary process in first differences. This is the case of univariate processes. Now let us consider what is the condition for stability and stationarity of VAR in the next class.